Hey everyone, how are we doing? Just getting some lunch, replying to some emails. Good to see you here, Branton and Jackson and Ivana and Sarah and Taylor and Elizabeth and Lindsay. Can we go over some chapter 12? We've done some chapter 12 during class. We can do some more chapter 12. I saw some people mentioning conditions. We got the hiccups. Saw conditions. Taylor, good to see you here. My headphones. I always hate when they're. I always hate when they're like a little bit twisted. No twist in the headphones. No. Who's thinking about it? Probability practice. Bunny's in the chat. I'll start with some probability practice. People want probability. If you vote so, we can do conditions again. We did conditions this morning, but we can do them again. Probability we did during class. We can do it again. We got this. Let's practice chapter 12. Probability. Let's go do it. Okay. So when it comes to probability, let's go for the very basics again and review. Two events that can be easily added together are what? Two events that can be easily added together are what? Remember, the formula sheet's going to have hints for you. Yeah, we can do some sample stuff. We've got here condition, sample, definition. Two events that can be easily added together are disjoint. Good job right there. They are disjoint. So when we go right here, we've got the formula sheet up. Two events that can be easily added together are disjoint, and you see the addition rule right here with the mutually exclusive, which also means disjoint. Those are just synonymous words right there. So the formula sheet is going to be a good review to see it right there. So when you think about events right here, some of the easier questions, like the level 1 questions, I would say would be like, someone could win a trip in a lottery to go to New York or CA. The probability of their ticket winning New York is 0.2 and CA is 0.03. What is the probability they win one of the two trips? Now, we kind of have to assume this about it. We'll do those here. Taylor, good question. We'll do that here coming up. The good question, Taylor. We can do that next. Because I know you asked that at the start, so we'll do that next. You got it. So what is the probability they win one of the two trips? And those are as proportions, so we could say 2%, 3% if we wanted. 2%. It's like a expensive lottery if you're going to have that probability. 3%. So this right here is very clearly the what rule. So someone could win a trip to New York or California. The probability of their ticket winning to New York is 2%. The probability of winning California is 3%. So this is assuming you have a ticket, and the ticket could either win for New York or California. So with this right here, and you see the or word was probably they win one of the two trips. So it'd be probability winning New York or California. So what would it be? It'd be 5%. Great job, Elizabeth, right there. So it'd be a 5% probability. What is the probability you do not win the New York trip? What is the probability you do not win the New York trip? What is the probability you do not win the New York trip? So it'd be like, not winning the New York trip is the complement of winning the New York trip. So you either win the New York trip or you do not win the New York trip. So what's the probability of not winning the New York trip? Because winning the New York trip is, so not winning the New York trip would be what? Because you either win the New York trip or you do not win the New York trip. 98. Does that make sense? Because that would be the complement. Because you'd say you either win it, 2% probability you win it, or you do not win the New York trip. So now this is interesting though. Let's try this. What is the probability with one ticket you win the New York and CA trip? Let's say right here, tickets can only win one trip. So now this one's tricky. The previous one was 98%. So this one says, what is the probability you win the New York and California trip? Now, before solving anything, great work, Branton. Now be careful though. Before solving anything, what do you have to think about? What is the probability you win the New York and the CA trip? Before solving anything, what do you have to think about? What do you have to think about? I've underlined a keyword. What do you have to think about? Well, it's going to be the multiplication rule, right? And we can only multiply things when what? We can only multiply things when what? It is the multiplication rule. We can only multiply things when what? When they are independent, right? So if somebody won the New York trip, What would you know? Like someone's like, I just won the New York trip on my ticket. What would you know about them winning the California trip? What would you know? This is a trick question right here. Like it's a tougher one trick question. So if someone just won the New York trip, what would that mean about them winning the California trip? What would that mean? They're not going to New York. So, or California, excuse me, California. They're not going to win the California trip because you can only win, tickets can only win one trip. So we're going to tell, like the scratch off ticket or whatever it is can only win one trip. So what is the probability of both occurring then? So don't even worry about the math on it. Think about it theoretically since they're very dependent. If one, they are disjoint. If one occurs, the other can't because we already established they're disjoint up here. If one occurs, the other can't. So what's the probability of both occurring? If one occurs, the other can't occur. So what is the probability of both occurring? Don't worry so much about the math. Think about it theoretically. It's 0. Because if one occurs, the other can't, which is the idea of disjoint. Does that make sense? So be very careful with disjoint, independent. We did a lot of review on this in class today. Check out the class video today where we went over and did each definition. If you could win both, how would you do it? So let's say we have something like you are selecting jelly beans and 20% are those gross jelly beans that no one wants to eat. So they're like I don't know, like what are they like the fish ones or like I don't know, they have like weird flavored jelly beans, those Burt's Bees, what not the Burt, I don't know. The Bean Boozled. So the Bean Boozled jelly beans. What is the probability both your jelly beans are gross? So I'm fine with toothpaste. Dead fish, no. Toothpaste, I'm toothpaste all the time. I'm toothpaste every night, every morning. I'll eat it. You can make here's a toothpaste jelly bean. I'm not gonna be like yay, but I'll eat it. It's not that big of a deal. Like, would you rather eat 5 toothpaste jelly beans or 1 spoiled milk jelly bean? That answers the question. Or 50 toothpaste jelly beans. Now I don't want to eat that much jelly beans. I'm gonna just swallow the spoiled milk. 5-1. It's a 5-1 ratio for me. So what is the probability of both your jelly beans being gross? So you have to think, this jelly bean was gross, and I grabbed it out of a big bag. Does that influence this jelly bean of being gross? So think about this. So first jelly bean gross. First jelly bean gross. And gross. And second jelly bean gross. That is the probability right there. Yes, Branton, exactly. Great work. And so what did you have to assume about the jelly beans right there when you were doing the multiplication right there? So Branton has the mathematics. And so what did you assume about the jelly beans right there when you were doing this? Exactly the mathematics. That's great to do it. Mathematics is correct. And what are you assuming about the jelly beans? When you pick up this jelly bean and it's gross or good, the second jelly bean is completely what of it? So this is, you have to think, this jelly bean was gross. Does that tell me anything about this jelly bean being gross? You got it from a big bag, like huge bag. There's just, I say 20% from this company are gross. You say, okay, let me just take one jelly bean here. Let me just take one here. They're completely independent because if this jelly bean is gross, it's not going to influence this jelly bean over here, right? So you just reach in, grab 2 jelly beans out of this crazy huge bag. 20% from the factory, which is an even bigger sample, is gross. Like that's how they make it from the production line. We know the true probability apparently. So it's not going to, if you sample without replacement, then you could say, well, then if one was gross, the other one's less likely to be gross. But in this example, we know from the company that 20% are gross, and we have a big bag. So we'd say, well, this one's gross, 20% probability, and then the next one has a 20% probability of being gross. It's not going to increase or decrease the probability of the next one being gross if this one I have right here is gross. So this is the example of independent. Are these disjoint or not disjoint things? Are these disjoint or not disjoint? So you have to ask, could the first jelly bean be gross and the second jelly bean be gross? And that'll answer disjoint, not disjoint. Are they disjoint or not disjoint? They are not disjoint. Because not disjoint means if one jelly bean is gross, then the other jelly bean could also be gross. So they're not disjoint because they could, and so we can't add them, correct. And think about this, because think about how it could go wrong if we use the rule of addition. What's the probability your first 6 jelly beans are good. Now, if you use addition rule for this, let's look at the wrong way. Wrong way. First is good, or second is good, or what's going to happen? We'll raise up. Oh, we can just do this. First 2 jelly beans are good. Your first 2. So this is first is good or second is good. And what are you going to notice? This is the wrong way of doing it. So you wouldn't do it this way. And this is your first is good or the second is good. So Brandon, you are doing it correctly. You're doing it the correct way because this is the wrong way. And and Elizabeth, you are doing it correctly. I can't trick you guys today. Guys, say for everybody. I can't trick you because this should be multiply. The right way is to find out first good and the second is good. And that would just be the multiplication of probability of good times probability of good right there. If you do it this way right here, the OR rule states that they have to be disjoint. And what do you notice immediately about this to tell you you've done it wrong? What do you notice immediately to be like, yeah, I think I did something wrong? What do you notice immediately? You've broken a rule right there. So beyond it being the wrong way of doing it because they're not disjoint, because the first could be good and the second could be good, it's outside of 1. So probabilities are contained between 0 and 1. So if you obtain a probability like that, you're like, nah, probabilities done as decimals are between 0 and 1. So that is not a proper probability. I want you to describe this in words. Both my jelly beans were good, right? I was going to ask you to say both my jelly beans are what? This is the first was good and the second is good, right? So what is this? It's the complement of it when you do 1 minus. So either both your jelly beans are good, no negative probability. Someone talked about, someone mentioned in class, there were like pseudo probabilities or something. There might be some super advanced math concept, but I'm not aware of it, Branton. There was a student class talking about it, and I was like, really? There might be some high-level real analysis, partial differential equations or something weird thing. Upper-level math gets very weird. But probabilities are contained between 0 and 1. 0 means never occurs. 1 means 100% occurs. Then there might be some weird mathematics that break rules to do things that are imaginary. Like imaginary numbers. You can't give someone an imaginary number of jelly beans. Put it that way. When we work with like outside of mathematical theory, there's some really crazy mathematical theory. And that's not what I teach. I teach the application of everything we do. How would this be described? This is all jelly beans are good right here. So this would be all jelly beans are good. Now, this is the complement of it right here, which means not all jelly beans are good. So all jelly beans are good, and that's the complement which says not all jelly beans are good. I know, right, Brandon? How did we get 0.8? Because either a jelly bean is gross or it's what? To Ivana's question right there. And Elizabeth, that is correct. How did we get 0.8? Because either a jelly bean is gross. We're only going to have 2 categories of jelly beans. So how do we get the 0.8 right there? Because either the jelly bean is gross or it is what? And so how did we mathematically get the probability of good? 1 minus 0.2. Great job, Branton. We got to throw you a lot of points, Branton. Let's throw you some 5,000. Keep up those answers. Keep up the practice. That is the complement. Either of jelly bean, according to this example, is gross or good. You could say gross or not gross. Like, it was a not gross jelly bean. Like, it was good, apparently. We're just going to say either it's gross or good. So the probability of 2 good jelly beans is 0.8 times 0.8. And right there, because they don't want to give you all gross ones. Imagine if you bought those Bean Boozled and like there was only one good one. You'd be like, I'm not eating these. They only throw you like a few of the gross ones to be like, oh, you don't want them. Because if there are like 2 good ones, then they'd be like, no, you don't want that. They probably were. I don't know. I wonder if they do research on that to see if people will eat it or like it. They probably did some consumer research to figure out the optimum true proportion of grossness to have in there. And I wonder if they are very exact. That's interesting. I'd love to. I wonder if we could go talk to them about that. I'd love to know how the process behind that and the decisions made of the true proportion of gross. I should contact them. I wonder if they would talk to a stats class about it. So either all the jelly beans are good or at least one is gross. So the probability of at least one gross is 0.36. Does that make sense? Because if you mathematically solve this right here, this is 1 minus 0.64. And that is equal to 0.36. So the probability of at least one gross one is that. And do you know what happens? What's interesting? I'll show you this really quickly. What's really cool and what we can do, and this is why I like business analytics, is because I was thinking about this theoretically. So what we have right here is we have eaten jelly beans. And the amount of jelly beans you eat, you could eat from 1 to 100 jelly beans. And then the probability of at least one gross is always going to be the formula 1 minus all good jelly beans. So we need to raise this to the vector eaten jelly beans. And there's the associated probabilities. And what do you notice about the probability if we plot this out right here? As you eat more jelly beans, it's x comma y, right? I don't usually use native plot. As you eat more jelly beans, what do you notice about the probability of at least one being gross? As you eat more jelly beans, what do you notice about the probability of at least one being gross? As you eat more jelly beans. Is it type equals line? There you go. What do you notice about the probability of it? The probability of it starts to do what? The probability of at least one gross jelly bean. Well, it does kind of flatten out, but it approaches what? As you eat more jelly beans, and here I'll do this, we'll rewrite the vector. Let me, it'll probably be easier to see if I don't go to a crazy amount. If I just go to 10 jelly beans, which is more than enough, what is the probability approach? It approaches 1. As you eat more jelly beans, the probability of at least one being gross, which is the probability right here, you see the probability of there being gross with one jelly bean is 20% because there's 20% gross. But then it starts to increase and go up. That's the 36% we found right there. And it starts to go up, 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 up. And if you keep going out on this curve, it's basically virtually impossible that you would not have a gross jelly bean. The probability approaches 1. It's just basically virtually impossible to keep eating those jelly beans and not run into a gross one. Like after it's just bound to happen basically. But your next jelly bean at all points has a 20% probability of being gross, but the probability of you going on like a 30 jelly bean streak without having a gross one, because we could just inverse this right here and we could figure out the probability all good. So the probability of all good jelly beans is going to go down. So now this is just the probability of all good jelly beans. And so there's the probability of all good. So if you eat one jelly bean, it has an 80% probability of being good. And then as you eat more jelly beans, the probability of all the jelly beans being good is going to decrease. And then the complement of that is, you see how these are just reverse curves of each other? So that's why the curves kind of go in reverse right there. Yeah, I should overlay those. That'd be neat. But I hope that brings some extra understanding. And that's why I kind of like doing coding, because you can just be like, oh, wait a minute. If I use that equation and just plug in a vector of numbers, then I could just solve out each one of those. On the practice exam, can we go to the first question? It's about probability. Yeah, here, let's do that. Let's do, well, there was one question about conditions, and question 1, practice exam probabilities. And if you're looking for practice exam, the practice exam, I go over each question on the review 2 video playlist. But let's do the conditions right here. Wrong button. let's go do the conditions. Conditions for sampling distributions. Okay. Conditions. 1943. Stat 201. I think everyone knows we're doing Stat 201 today. And let's go check it out. Okay. I'm trying to trick you right here. Be ready. Chapter 7. Condition 1 for Chapter 7 is what? Chapter 7 is regression. We're going to do some 13, 14 here, right here. This is Stat 201 currently, yep. Ask any question you got. Chapter 7 is what conditions? There's Chapter 7 on the screen for you. QQ, straight enough. No outliers. Plot doesn't thicken. Now we're talking about the residual plot. QQ, straight enough. No outliers. Plot doesn't thicken. That plot, I don't know. It looks about the same thickness, but there's some whats. What do you notice is problematic about this regression with the QQ, straight enough? No outliers. Plot doesn't thicken. QQ, 2 quantitative variables. Straight enough. The line goes through the middle of the data. It's straight enough. Doesn't bend around it. No outliers. Huh. Got some outliers. QQ straight enough. No outliers. Plot doesn't thicken. Plot thickening looks to be all right on this. The plot remains relatively the same thickness. Does that make sense? The issue is more these outliers over here. What's neat is you can actually go here and go to rows, invert selection. Then you can go right here and go to rows, markers, big markers, rows, colors, red to mean scary. And now we've marked all our residuals so we can see, or the ones that are extreme. It looks like, yeah, there we go. Whoa, there we go. There they are. So, excuse me. Those are the values right there. Do you know if there will be a curve? There could be a curve. It could be. Good to see you, Ethan. And there could be. We'll find out. So we have some QQ. What does QQ mean again? Type it in the chat. You have to ask, are X and Y quantitative variables? So probably don't write QQ if, I don't think it's a written question, but you'd probably want to say 2 quantitative variables. We memorize it as QQ. Straight enough means straight line approximates relationship. No outliers is what it says. It says no outliers, no extreme values away from line. And plot does not thicken. Plot, residual plot. You can look at the regression plot. We look at the residual plot a lot of times. Residual plot generally doesn't thicken. What should a residual plot show? What should a residual plot show? So what should a residual plot show? Answer that while I'm making this look all nice and pretty right here. See if you can write these down and describe them. That's where the real learning takes place. What should a residual plot show? Which this one... shows the outliers. A good residual plot should show what? Absolutely no whats. Is this a good residual plot? Is that a good residual plot right here? Is that a good residual plot, yes or no? So it is. It is very good. It's very good. Because residual plots are when you take the line and make it flat. So if we had a model, the model would be a line, and then the points would look like this. And then you simply take that line, and you make that line flat, and that's what the residual plot is, to tell you the positive or negative difference above or below the line. So if something is above the line, positive residual. If something is below the line, negative residual. If something is on the line, zero residual. It tells you how much things miss by, i.e. right here's your zero residual, as we see over here. So it's just a really quick way to view all the residuals, and we should see no patterns. No patterns is a good thing. I know that sounds crazy, but...
I am Ubot.
We deleted the approved. That was supposed to be approved noise, but we don't have it.
It doesn't matter!
Oh, thank you, Rock. We appreciate that. So... this is a good residual plot. But now we get to the new conditions for chapter 13/14. Chapter 13 has condition 1 what? This is sampling. Sample proportion. What is the first condition for chapter 13? Randomly select your data points. Randomly select your data points. Think about this. And I encourage everybody to vote. Please encourage everyone to vote. Encourage your parents to vote. Encourage your friends to vote. Encourage the people you don't like to vote. I even encourage the people I disagree with to vote. Someone says, I think you're wrong on blah, 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 Brian. I say, well, go vote. We'll figure this out at the voting booth. I mean, personally, I want the people I agree with to vote more, but I do encourage everyone to vote. Please vote. Everyone vote. Please clap. That's a 2016 joke. 2016 political jokes here. So my references are going to get even older as I get older. So with that right here, think about this. You ready? If it is true, and I want you to pick Republican or Democrat, that 40% of UT is what? If it is true, I want you to pick Republican or Democrat. And I'll tell you why the first condition matters right here. If it is true that 40% of UT, and someone put Republican or Democrat, or you put Green Party, Libertarian, Reform Party, what else is there? Whig Party. What else is there? Like all these old school parties. What party? If it is true that 40% of UT is this is this chapter. You have to know the truth in this chapter. We let's see, because that's the old school party, right, Elizabeth, right there. 40% of UT belongs to party W. Okay. So you go and you sample UT students. What percent of UT students would you expect to be part of party W? If you just take a sample of 100 UT students, your sample size is 100 UT students. What percent, or we could do 200 because that makes the numbers a little bit more fun on the later portions. What percent of UT students would you expect to be part of party W? This is the truth. 40% of students belong to party W. What percent, I'm going to go grab, I can just go to the formula sheet. What percent would you expect? 40%. And you've literally just done this first thing right here. You've just done the mathematics right here. That if 40% is the truth, you would expect to see 40%. That's what that formula says right here. This says when you take a sample, you expect to see on average, that's the average for samples, your average sample should be this. If you were to average up your samples, you would see that. The center of the distribution is the mean of the distribution, and it's probably best to read this at times. My expected sample proportion is the truth. Because if 40% of UT is part of party W, well, then I expect to see 40%. But think about how the random condition plays a role here. If you go and hang outside one of their conventions, one of their parties, then you go and sample 200 students outside their party. Like you go to a convention where they're meeting and you sample 200 UT students at this. What condition have you failed, and why would it not follow the distribution it's supposed to? So if you go outside their convention and ask students what party do they belong to, you're like, oh, there's a political thing going on tonight. I'll go hang out outside that and ask people what party they belong to. So you go outside their convention and you ask UT students what party they belong to, and a bunch of them are like, oh, I'm party W. And you're like, oh, well, wow, a lot of, didn't expect that. I expected 40%. You went outside the convention to ask people, what condition have you gotten wrong right here? What condition have you gotten wrong? And why is it not following what it's supposed to follow? It's not really response bias. Response bias is if you were to word the question, but like, do you really think you should be part of that party? No, like you're trying to elicit a response. The first condition is random. So if you go to talk to UT students, you should talk to what UT students? If you go to talk to 200 UT students, you should talk to 200 what UT students? If you go to talk to 200 UT students, you should talk to 200 what UT students? Well, no, you're going to talk to random UT students, right? You're asking what party are you a part of? And you'd expect 40% to be part of W party right there, right? So think about this. If you go outside of a convention for that group, are those random students? So you're now going to go outside a convention and talk to students there. Are those random students? No. So then you haven't met the randomness condition, so you won't see what you're supposed to see given the truth exists. So that would be where we don't, and it's kind of convenience. Good, Jackson, great answer there. It's kind of convenience bias, or yeah, I'd say it's convenient. Good. Actually, I could throw you 5,000 points for that. That would be a good example of convenience bias. Like, well, I don't know, they're doing a convention. It's probably an easy time to talk to people, and they'll probably want to talk to me about politics because I'm getting a lot of what right now when I walk up to people and they walk away from me. We're covering multiple chapters. It's going to be easy for me to go to the convention and talk to people. Right now, I'm like, hey, do you want to talk politics? And they're like, no, I gotta run. I don't got time for this. I'm getting a lot of what right now from people when I try to talk to them about this. I'm getting a lot of what. This is some chapter 10 questions right here. Right now, I'm getting a lot of what. I'm like, hey, I just got a few questions. That would be people running up to talk to you. Be like, hey, you're doing a political survey? Ah, love that. You might get more voluntary bias when you're at the convention. You're probably getting non-response bias when people refuse to talk to you. So they're kind of the opposite. Caden, great work too. They're kind of the opposite of each other. When people don't talk to you, that's non-response bias. When people want to talk to you, that's voluntary bias. So they kind of work the same way. That voluntary bias is when those who volunteer their opinions have strong opinions towards one side or the other. They're like, man, I hate that party. Oh, I love that party. Where non-response bias is people who don't respond differ in their opinions than those who do respond. So non-response bias literally means people are not giving you their responses. So a lot of surveys probably have non-response bias because especially these days with people who don't want to do surveys on the phone, I will not do any survey on the phone. especially because scammers and stuff will want to get you hooked by asking you easier stuff, and then you'll have like your like buy-in. What is it called? Sunk cost fallacy is I'm thinking of. Like you're like, well, I've already talked to them for this long. I guess they know so much. Sure, here's everything you want to know about me. So be very careful, especially with all the scammer calls. Be very, very careful. PSA from Brian right there. So the first condition is random. The next condition is what? What is the next condition? Sunk cost fallacy. Javen, thank you so much. We're making you a mod, Javen. So the next condition is what? Condition 1, random. Condition 2, what? 10%. And what do we mean by 10%? And how would we check this? How would you think about this condition right here and check it? We have a formula we use all the time to check this. I think a lot of times you just think about it theoretically. Remember, we're talking to UT students. So it means less than, right? Less than 10%. So do you think we pass the condition right now or don't pass? And great job, Elizabeth. Elizabeth wrote the formula little n over capital N. That capital N does not stand for normally distributed, it stands for population size. The sample size is less than 10% of the population size. You're thinking about success failure. I think Jackson coming up here in a moment. So explain to me why we do or do not pass. Explain to me why we do or do not pass. Explain to me why we do or do not pass the 10%. The 10% condition states we need to sample less than 10% of the population. So no more than, less than. That's what we want. So talk to me about it right now and tell me, we went out and talked to 200 UT students. We went out and talked to 200 UT students. So what do you probably need to think about for a moment? So we know 200, right? What is something you should be thinking about? Yeah, Jackson, good work right there. I got through some words. So I think, tell me if you're seeing it right here, Branton. So this passes the success failure condition because, oh no, excuse me. I was thinking success failure. I was thinking the next condition. Right. It will pass that too. This passes the less than 10% condition because 200 UT students is less than 10% of all UT students. Does that make sense? You could kind of go off of some theoretical values like Lindsay and Jackson and Elizabeth are doing right there. Oh, you're thinking the 40 out of 200. Yeah. So 40 is P, and the what you're thinking about. So theoretically speaking, if you think UT is, there we go, 30,000 students, people are doing the math, and you want that to be less than 10%. So just kind of going theoretically, we want it less than 10%. It's a very odd condition. It works with finite populations and the buildup of error. That's more like mathematical theory, advanced stuff. But there's more errors in calculations due to classical statistical techniques. We have advanced ways of doing this with simulations with advanced statistics, but for classical techniques, you can't find, you're not supposed to go beyond 10%. It creates error in the calculations. Don't worry too much about it. You just need to know how to check it, what it means. We're not going super high level on like, show the mathematical theory of the buildup of error at a 5% population versus a 10% and calculate the exponential growth beyond 10%. That's not where we're going. Take some advanced classes. We'll do that. I mean, I don't know. We don't do that. That's not business analytics. That's math theory. The last condition right here, what should you do before the last condition at all times? Before just saying it, be very careful. You'll probably get it right if you say it because it's the first one we learn for the new conditions 3s. But put them in the chat. You know what to do. Put them in the chat. We will be doing this for the remainder of the semester. We pause right here. We got some pause in the chat. Mubot, you want to put those pause in the chat, or I'll give you some pause in the chat. There's some pause in the chat. We pause right there. I should put pause also for pause, but we put some pause in the chat. Pause right there. Stop. What should we look at? We're doing categorical data. Since we're doing categorical data, we need at least this, at least this. Since we're doing categorical data, we need at least this, at least this, which I'm basically telling you the condition. Since it is categorical, so you pause, you say, what is the variable type? The variable type is going to clue us in, and depends if it's categorical or quantitative. Great job, Lindsay. Good review. So because it's a categorical variable, it's going to be the what condition. Because it's a categorical variable, it's going to be the what condition. Success failure, exactly. Success failure for categorical variables. Success/failure. What mathematics do we need to check for this? What mathematics do we need to check for this? So we need to find 3 quantities to check this. I mean, it'll be something, 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 but the thing is used twice. So what quantities are we going to use to check this? We need one more quantity, which I usually solve for right away. NP, NQ, great job right there, Elizabeth. So what is Q? I'm shocked. We didn't have people asking what is Q this semester. All people say like, wait, how do you find Q? We get every once in a while. Usually like day of test, was like, wait, how do you find Q? How do we find Q? P and Q are complements. Great job there, Lindsay. So Q is 0.60. And so is success failure condition met? So what is the variable that is categorical? So asking someone, are you part of W party is going to be a categorical question. Like, are you part of the party or not? Does that make sense? So categorical means it's groups, where quantitative means it's a numeric response. Like, what is your height? What is your weight? How much is your GPA? We should say like how much for quantitative. Like, how much is your height? I have this much quantity of height. How much is your weight? That's better. Sometimes we say what for them, but we can't say how much is your party. We would say what party are you in, or are you a part of this party? Like, are you part of this group? No, good, Brandon. Keep those questions coming. The number one thing is you ask the question, then you either affirm your knowledge or you fix your knowledge and you work with it right there to learn. So thank you, Branton, for asking all those things right there. Success failure condition is at least 10 successes, at least 10 failures. How many successes are we expected to have, and how many failures are we expected to have? How many expected, if you talk to 200 people, how many would you expect to be in party W? How many would you expect? $80. How many would you expect to not be? How many would you expect to not be? So think if you expect 80, then you expect 120 to not be. What do you notice is a really good check with these numbers? What do you notice about these numbers right here? It's like, oh, maybe we got to check on our work with these numbers. What do you notice about a check with those numbers right there? They add to 200. It's like, well, if I talk to 200 people, I'd expect 80 to be in the party and 120 to not be. So that right there is going to be our success failure condition, and we do meet it because we have at least 10 successes, at least 10 failures. So what happens if we don't meet the success failure condition, or if we don't meet these conditions? If we don't meet the conditions, the distribution will not be what? So this is, we talk to 5 students, and we expect 20% of the students to be in party W. Or we could do 40. Is it still gonna? It's trying to look kind of symmetric. Interesting things happen. Let's talk to 20 students. Really? Kind of crazy. If we don't meet the success failure condition, what happens? There we go, like that. If we don't meet the success failure condition, what happens? So this is like maybe Green Party, 5% of students are in the Green Party. So now it's skewed. It's not normal, right? It's not normal. So if 5% of students are in the Green Party and you talk to 20 students, answers on the screen also, how many students would you expect using this mathematic mirror checking the success failures NP times NP and NQ had to be both greater than or equal to 10. So how many students would you expect to be in the Green Party if 20 students are the amount you talk to and 5% are truthfully in the Green Party? How many out of the 20 would you expect to be in the Green Party? The answer is kind of on the screen. You have to think about NP right here. What is NP? So just so we'd expect 1, right? Good. So 1, because right here is the answer. What does representing when finding a success? So the amount successes mean like someone is what you are looking for. So if 5% of people are in the Green Party, we're looking for people in the Green Party, and we'd expect 1 out of the 20 people to be a success. Does that make sense, Jackson? So a success is just contextual based on what we are looking for. So it's not like, yay, Green Party. It's like, we're looking for Green Party. Oh, this is a success because that was the probability we were associating success with. Purely just, Rock would say,
It doesn't matter.
it's just whatever the probability is associated with. You could label it party libertarian or anything. I'm just thinking of smaller parties right now. No, what does A represent? When you say A, can you, what does A represent? What does A, like the probability of event A? Can you expand upon that, Jackson? Expand upon that and I'll answer. Keep up with those great questions. I'll try to answer, and 1,000 points right there. Keep up those. The last slide. You're talking about the right here? that's it. You might if that looks like an A right there. That's NQ. Just my bad handwriting there with Q. So that's NQ. It's just my Q's look really bad. So right there, that's NQ right there. It's my Q's are just it's my bad handwriting. Thank you, Jackson, for asking that right there. Please ask anything. My bad handwriting is my worst part about me. I can type super fast, but I can't handwrite at all. So my D's look like O's. No, Jackson, thank you for asking. I mean, what is NA? How do we find NA? That's the Q, just a shorter tail on the Q. So with this right here, as we approach 10 successes, 10 failures, what starts to happen to the distribution as you start to get more successes, more failures? The distribution starts to look more and more what? Yeah, and then we got to do some 320 also. So yeah, 474, question 5. Yeah, let me put that on here, and I got to put a little 320 on this. And let me put that here. And someone 320 wanted assignment 8, but I don't know what they wanted. They never said what they want. So I don't know what to do because this is that. Thank you, Alexander. We'll do that here in a little bit. It starts to look more normal. So meeting the conditions means it looks normal. But now let's talk about here the next set of conditions. Or let's do one more part of this. You ready? Would it be odd if 100 students in your sample were in, would it be odd to see 100 students in party W? Is it odd if 100 students are in W party? Is that odd? What are your thoughts on this? Is that odd? Well, it might be. What do we need to find for this? And great job, Lindsay, right there. It might be. Well, what should we probably find to figure out if it's odd? We should probably find it's what? To think if things are odd, we probably need to standardize it and find its z-score, right? So we need to go here and we need to draw the distribution. The distribution, never can say that word, will have a mean of what? The distribution will have a mean of what? What will the center of this curve be? So where is the center of that curve? The center of the curve for what we expect when we take a sample of students is what? The center of the curve is where? Where would the center of that curve be? Where is the center of that curve at? Where's the center of that curve at? 0.4, because that's where the mean of the sampling distribution is at right here. So where do you think we landed? In the green region maybe, or the red region? Where do you you don't have to say exactly, but do you think we landed towards the green or the red region? Just thinking theoretically about when we say we had 100 successes, which is X, and then X over our 200 sample size is going to be 50%, which is P hat. Do you think we landed in the green region or the red region? Which region do you think we landed in? I'd say we probably landed in the what region? So 40% is at the center of the curve. We landed at 50%. This is where we landed. So we're probably closer, what, to the green or the red? So we landed at 50%. Do you think we're at the green or the red? Which one of those seems like probably more likely where we landed? Not saying exactly where we landed, but probably around the green, right? Because it's above average. We're above average. So what else should we probably put on this curve? I'm going to start drawing it here. But we probably need to figure out the what's for this curve. What would be another good quantity to figure out for this curve? What would be the standard deviations, right? To figure out how far the unit differences are away on the curve. So we go P, which is 0.4. P times Q, which is the complement, over N. It's going to be about 0.3, is it? Ah, yeah, there it is. Ah, so it is. Anyone got a guess of let me double check. Lindsay got a different number for me. Let me check. P times Q over N square root. Lindsay, do it again real quick. And unless I'm doing something wrong, the N is 200. Remember, you might have done N 100 maybe. Got point. Yeah, Lindsay, thank you so much. Lindsay, we're throwing you 5,000 points for checking the work also. No worries. Can anyone estimate the Z-score right now? 5,000 points. Thank you, Lindsay. Right answers, wrong answers. We're here to practice. Can anyone guesstimate the Z-score? The Z-score is going to be about 2.96, I say. I'm going 9.4, actually. That's my guess of the Z-score. Because take a look at this. The standard deviation is 0.034. What do you notice about 50%? Nice job. It's over there. It's right before 3 standard deviations, right? So it's kind of close in my guesstimate of it because it's a little less than 3 standard deviations. So we take the observation. We do the mathematics. I'll put it below. The mathematics is p hat minus p. It's right there over the standard deviation. So we're using this formula right here. So I'm going to just write below it what the formula is. Go away. So p hat was the sample proportion, what we observed in our sample out of 200, minus what we expected given the truth. Then we divide by the standard deviation, which was 0.0346, I think, or something like that. And there it is right there. And then we have a 0.10 difference, divide by that. And there it is right there, 2.89. Great job. And so, yeah, that's just the Z-score right there for how many standard deviations, and that's our drawing. If it asked you to estimate the probability, and the probabilities were like, let's say here, 1%, 5%, 10%, 90%. So if this was a multiple choice question on the test, 1%, it's probably less than 1. It's about 0.5% actually. 10%, 90%. Which of those would you guess? So if you drew this down and said, what's the probability you see something as high as this? Think because the Z-score is basically 3. You would know from the normal curve that above here is 2.5, so it has to be less than 2.5 because that's 2 standard deviations, so 95%. So it has to be less than that. So the 1%. Does everyone see how we could ask theoretical questions? This was a really good review of almost the full chapter, basically, from the conditions. Are people feeling a little bit better? This is a lot of the conditions, right? We did checks on the conditions. We basically just did a full problem right here on how to do the work and solve out for each of the components for the conditions, for knowing what p hat is, the sample proportion. It all boils down to notation. We're going to do one more of these right here. So keep those questions rolling in. Here we go. We'll mark that as chapter 13. Chapter 13. Chapter 13 practice. Chapter 13 practice. Okay. And then we got chapter 14 practice right here. Try to look a little quicker on this one. Step 1, chapter 14 practice. Okay, here we go. With chapter 14, you are doing the sampling distribution of the sample mean. Very similar. So chapter 14 and sampling distribution of sample mean. So if you see sampling distribution of sample mean, where are you going to go immediately? Where are you going to go and look? To make sure you get things correct, where are you going to go and look? I want you tonight, if you see sampling distribution of sample proportion, sampling distribution of sample mean, where are you going to go look? You're going to go look at that formula sheet under review 2. Look at the formula sheet and be like, okay, wait a minute. I have to use these ideas to solve these questions. And there it is at the bottom of the formula sheet, the sampling distribution of the sample mean. And these ideas are what we are using to solve this question or to talk about this. Now, the easy part about this before I even write a question is, what is condition 1? What is condition 1? So the first condition when you do this, if you go out and talk to people and ask them a quantitative question where you already know the truth, the first condition is random. Randomly select those individuals. Randomly select those individuals. The second condition is what? The individuals you select need to be what? The second condition is that the amount of individuals you select need to be what? Which is the weird one. The one like, wait, what? I thought more is better. 10%, less than 10%, so less than 10%, no more than 10%, less than 10% of the total population. Good stuff right there. Now, what do we do? Put them in the chat. What do we do before we say condition 3? You know what we do. Take a deep breath. What do? Pause. Pause. We pause and we say, is this quantitative or is this categorical? So we're dealing with the sampling distribution of the sample mean. Pause in the chat. Love it, Ben, right there. Branton, sorry about that. And so what is the third condition right here? The third condition is, which relates to the nearly normal, large enough n, great job, large enough sample size. So we're going to do an example right here where we go through this, and let's see if we can solve this question. The UT registrar tells you that the average GPA of students is 3.6. You decide to talk to 100 of your friends with a standard deviation of 0.5, and it is very left skewed. And find out from your friends, most of which are honor students, that they have an average GPA of 3.95, 3.9. Let's go 3.9. That's all we need. Is this unusual? Check conditions and report if valid probability distribution can be calculated. Okay. Your thoughts on this? What are people's thoughts on this? So here's the question, and let's start right here. So we could start marking notation, or there's kind of an obvious thing I did with this problem right here. What are your thoughts on this to begin with? Do you catch the immediate, like, wait, whoa. Rewind time here, Brian. What's going on? There's an immediate, what's going on here with this? What's going on? What problems are there? The randomness, exactly. The randomness has a problem, because if you're going out and talking to your friends, most of which are honor students, randomness is not going to be met. So we didn't talk to 100 random people. So if this was, we used to write test questions like this as written tests, and then the whole thing, these would be like trick questions where it's like you're supposed to immediately be like, nope, can't do it. Like that's what we'd want. We would at least like throw in some extra stuff like here, like you decide to talk to 100 of your friends and find out from your friends, most of which are honor students. So yeah, you don't want to do that. This is no. You decide to talk to random people, and there we go. There we go. Okay. So now you decide to talk to 100 random people, 100 random students. There we go. Not just people. And so this is random. Condition 2, how do we check it? So a lot of people a lot of times forget how to do condition 2. This one doesn't show you the values you need. But what would you do right here? If you could, you would like to know the value of what? We need to look at the size of our sample over, what is that? How do we check condition 2? Great job right there, Lindsay. So if you can calculate it, or could think about it theoretically, you'd say, well, your 100 sample of 100 students, that's population size right there, is less than 10% of the population. And you can show it mathematically. And you can also think about it theoretically that 100 students would be less than 10% of the total population of UTK. So the formula to check this mathematically is sample size over population size, as if you've sampled less than 10%, and we do pass that condition. So the last condition is the large enough n condition. So to check large enough n, there's 3 steps. The 3 steps are, 1, what is the shape of the distribution? 2, what size? Oh my gosh. Oh, really? It's changing that. What size do we require with this shape? 3, do we have at least this size? Okay, upsample. So to check the large enough n condition, the first thing you need to know is the shape of the original distribution. What is the shape of the original distribution here? What is the shape of the original distribution here? Left skewed and very left skewed, right? So what is the shape of the original distribution? Very left skewed. So if it's very left skewed, you need a sample size of what? So if it's very left skewed, so we have normal, skewed, $100, exactly. So we've got all the numbers on the screen right here. So you check the shape of the distribution. It's very skewed. So now what is the size required? What size is required? 100. Notice the more skewed it is, the larger n needs to be, hence the name of the condition. Large enough n kind of works against the skew to normalize via the central limit theorem. Do we have at least that sample size? Do we have at least that sample size? Do we? Do we have at least that sample size? Is our sample size, is the n large enough? It is large enough right there. So this means we meet all three conditions right here. So the large enough n has the 3 steps. What is the shape of the distribution? What number do we require for that shape? How big of a sample? And do we have at least that sample? So let me ask you this. Is a sample size of 2 large enough such that the distribution of sample means of size 2 will be normal down here? Ask yourself the questions. What is the shape of the distribution? What is the required size? And then is 2 large enough? So what is your answer here? Is 2 large enough such that the distribution of sample means of sample size 2, which is when we take 2 observations and then average them. If you want to see from the start again, you take 2 points and then find their average. That's a sample mean. Notice how that landed right on top. That's going to be the average right there. That's going to be the average right there. That's going to be the average right there. Just go between them and you can find the average. It's going to be the average there. Is this a large enough sample size right here? Is that a large, yes or no? Is that a large enough sample size such that this distribution as I build it will be nearly normal? Is it a large enough sample size? That is correct right there, Lindsay. That is correct because the original distribution is normal, so the required size is 1. Since the original distribution is normal, then, and Lindsay, 5,000 points. Great job working with this today, knowing that the large enough n condition says that you need to look at the shape of the distribution. Since you said it was normal, then you don't need a large sample size because the original is normal. This is just more normal and also tighter by a factor of square root of n. The two things the central limit theorem says, that the new distribution of sample means will be more normal and tighter by a factor of square root of n. But how about this? Will the new distribution down here be normal? Look at the original distribution. It's skewed. So now as we do sample means of size 2, is the new distribution normal or not normal down below? And that's the answer to the question. The answer is most definitely what? Because now the first one was skewed, so is 2 large enough? No. We'd need a larger n right here, and 25 is probably large enough such that the distribution of sample means. And every single point down there, so every single point on the bottom would be the mean of 25 random observations up top. So you take 25 random observations, and then the 25 random observations find you the average, and there's it right there. And you repeatedly do the process to create a distribution of sample means, and there should be less skew down here, and it should be pretty much normal, probably about at 25. So with this right here, we'll finish off this question. So is this unusual? And let's do that. That makes it a little bit interesting. Okay. Is what you saw in your sample unusual? So what are you probably going to do if you have to solve a question like this that doesn't require conditions? To solve a question that requires conditions requires you to start doing the what. So now we're asking, is this unusual? We're not doing conditions here. What do we need to probably start doing? I changed the numbers to turn it into kind of a easier / tricky question. Caden, great job right there. Caden, that's right for 1,000 points. A z-score. We're going to start looking at z-scores here. And how can we start to help ourselves with solving for the z-score? Caden, good work right there. How are we going to start solving for that z-score? What are we going to start doing? Channel your inner Leo. What are we going to start doing?
Notation, brother.
We're going to do some notation. Whoa. Okay. Branton, so close. Brandon, I gotta throw you some big points for that. Brandon, you're so close. Think what you told me right there. You just told me that what you observed was below what you expected. So double check. You're so close, and you did really great work right there, Branton. But what you told me is what you observed was below average. I think you'll be like, so you did great job, and you didn't use the original standard deviation. If you also notice, I used a perfect square, and that's 10, So we'll see this right here in Branton, great work. So what you observed was above average. Does that make sense? Like, as you look at this right here, to be like, wait a minute, my sample mean, which is right here, this is the sample mean, y bar, because that's what I see in my sample of size 100. So that's the sample mean from the sample of 100. This is the truth for the university, and this is the standard deviation. And so now we need to figure out the new standard deviation to solve that formula up there. The new standard deviation, can I move this down? Yes, I can. And great job, Lindsay, on the z-score of 10. That is correct. So 3.9, we're just solving below it, the formula. The hypothetical mean right there, that's what the mu naught stands for, the hypothetical. The new standard deviation is 0.05, correct, because the original one was 0.5. Divide by square root of 100. Perfect squares are nice. And that means the new standard deviation is 0.05. That's what we divide by over here. Put that little window there, 0.05. And then we take the new mean, the mu y bar, which is just going to go over there for the mu naught. And we're going to put right here mu, which is 3.4. So the mean for the distribution of the sample mean is equal to 3.4. And that equals up to 10, because it's just going to be 3.9 minus 3.4. Let me ask you this question. Is it odd for one student to have a 3.9 average? Is it odd for one student to have a 3.9 average? Is it odd for one student to have a 3.9 average? I don't think we throw trick questions like this anymore, but is it odd for one student to have a 3.9 average? Why or why not? Is it odd for one student to have a 3.9 average? No, and why? Because for one student, that would only be what? So think about, you could actually change the formulas right here and solve it for one, but just think about looking at the numbers right here and think about one student and look at that right there for one student. Well, not 0.5, very close, because one student, a 3.9 would just be one standard deviation above the average. Does that make sense? So, and it's also not normal, but still it's not that far away, because for one student, it's just one standard deviation above. 3.4 and 3.9 are one standard deviation away. Does that make sense, Brandon, seeing that right there? But for 100 students having that average, that'd be like, whoa, that's really high for like 100 students to have that average. So that's where the original distribution might look something like this, where 3.9 may be up here and 3.4 is about at the center due to the left skew. But on the new distribution, 3.9 is going to be way off the curve. So the new distribution is going to be tighter and more normal. Yes, that's why it's like, oh, it's not that weird for one student to have a 3.9, but for 100 students to have a 3.9 is like over here and is way off the curve, because this is the parent, like the original single observations, and this is the mean distribution for the distribution of the mean, which is, I hope, like, this makes perfect sense to me when I see it right here. That's so cool. Yeah, because you're averaging people. You're saying like, well, what's the average of 25 students? Well, if this is like test scores right here and there's some really high scores, then they would average up to like this. Yeah, it's a really good theoretical chapter. Like if you get it down, you're like, boom. And it's really about that notation. So it's the average of 25 observations. I think there were a few more questions. We got to do some 474 sample definitions. I might just might reference. So for sampling definitions, wait, review. My best is this actually put a BS 340 in terms of subgrouping and plans. Oh, good questions, Alexander, right there. Alexander, you got those pro questions. Because there are some. What chart are you thinking about, Alexander? Like, isn't there like an NP chart? Well, the NP chart changes the boundaries based on each group, right? So I bet you Charlie, who's absolute pro, the central. Oh yeah, central limit theorem, of course. Your central limit theorem is everywhere. Oh, you're saying it is actually really applicable to 340. Yeah. Charlie Quick is awesome. Yeah, no, it's super applicable. Central limit theorem, because then we can model things by a normal curve. That's what the central limit theorem allows us to do. Alexander, and keep up the great work. Thank you so much. And then we'll do some 474 here in just a second. I'm going to point to these videos right here. If you want to go over the sampling methods, definitely check out these videos. Can we view on YouTube? Definitely check out these videos right here.
Pushing them towards something
Where
we want.
Brian explains all the things right here. Oh, wow. Look at how old this is. Wow, this is 2016. 6 years ago. Look at that. This is like how the Simpsons placed people by order of maybe importance. Oh my God. There's Jeb Bush. There's Trump. Hillary, Bernie. Marco Rubio? Ted Cruz? I'm the nice one. Is that Governor Ohio? Oh man. Who is John Kasich? Is that John Kasich? Is that Herman Cain? Herman Cain, John Kasich, Jeb Bush, it's Ben Carson. Oh, it is Ben Carson. Dr. Ben Carson, right? So that's Dr. Ben Carson. That is correct. Anyone else? That's Marco Rubio, right? That's Marco Rubio. Is that Ted Cruz? That's got to be Marco Rubio, right? You see, if you have something iconic about yourself, it's a little easier to recognize who you are. Got to be Marco Rubio, right? Ted Cruz. Because they were running with him, right? Ted Cruz is the middle. Ted Cruz right there. Yeah, man. Please clap. They give him. You think about the bias right here that you could give towards individuals like Jeb Bush, right? Jeb Bush. He's got the most sour face on. He's just like unhappy. Maybe that's how he normally. Yeah, cool stuff right there. Good stuff. Please vote at all times. So check out these videos right here where I go over the sampling methods. Also, if you want the speedrun videos, are going to go over the sampling methods. Also, be checking these out. Chapter 10, Davey 504 challenge. Oh my God, what have I done? Why did I challenge Davey 504?
Epic. Epic Stat Tool 1 speedruns of statistics. Brian Stevens versus Chapter 10 Sample Surveys. Begin.
Okay, when it comes to sample surveys, we need to use our note cards here. I'm too
Use
low there.
Quizlet, flashcards,
We're in the same
or
shirt.
something, because this chapter is a lot of memorization.
That's your hair, Brian. Your hair's
When you
too
have
long.
things like a population and a sample,
So check these out right here. What is it? Did YouTube do this? What? No way. I think YouTube did this. Or did I do this? Did I put those in? Did I do that? Wow. Yeah. Check it out. That's going over all of them right there. So if you want to hear about cluster samples, systematic versus cluster samples right here, I'd say it's a great way to review, and it's a no joke review. So we're gonna do some Fall 74 to end off right here. Got a meeting in a little bit. Fall 74. Let's go check it out. Thank you so much. You're welcome, Branton. Excellent work. Good luck on the test tonight, everyone. Let's do a little 474. 474. I can't believe it's another week almost over. Time flies. The question was 474. Question 5. Alright, whoops, I'm in the wrong class. Wrong class. Assignments. Tree-based models. Data sets. You need to sponsor by G Fuel. That'd be funny either, right? Same this week's flew by. I know, right? Get that G Fuel sponsorship. I don't know. I need to try G Fuel first. They just did some stuff with Binding of Isaac, which is one of my top favorite games. So, I don't know. I'd have to talk to UT before I ever had conversations like that. You never know. Never know. If G Fuel said they'd sponsor me, I don't know. I don't actually. You know what? I don't think I'd take it. One, it doesn't matter how much they'd pay me because I don't want. I think there's better ways to spend your money than on G Fuel. Like, sorry, maybe G Fuel tastes really good, but money-wise, it's probably just not worth it. And I don't want to promote things to students that would have them spend money not wisely, so I wouldn't promote it. Sorry, G Fuel. Sorry, G Fuel. Probably better buy Celsius. Yeah, it's another energy drink, right? Brian's favorite Mewbot Madness drink. Oh man, no. You see, you can't do that. See, if they came to me and they were like, "Hey, we'll make a flavor after your channel" or something like that, like, of course they would. I mean, it doesn't probably take. I mean, they can just print labels, so they have a print. They can just. That's why it's so easy for them to do it, and then they just keep like Taco Bell releases like the Taco Grande Extreme with lava sauce, dude. Lava sauce. You want to know how much I'd go to Taco Bell with lava sauce? Can you explain how to do the math for the tails and which things, Jalen, right there? Can you explain? We'll do that next here. Let's go here and do some False 74. Let me know which thing you're wondering about. We're going to do a little False 74 right here. You get to see a little business analytics. Here we go. Here we go. Here we go. Here we go. Question number 5 on 474. Where's your homework? Okay. Keep waking up early because my piercing was broken. Question 5. Watch this. Question 5. Okay. The following chunk creates a decision tree using different subsets of the original data, characterizing the customers that have the highest probability of buying. I'm looking for something like customers who spent more than 900 and visited at least 7 times in the least 90 days. Is this what you're... and so this is where the mods jump in. Watch this. How to use around this channel. There we go. There we go. Mods. We do the mod thing. The following chunk creates a... Is this one you're talking about, Alexander, right here? First question. Oh, the first question on the practice exam. We can do that here, Jalen, after this. So is this the question you're referring to? Purchase not found. What? Purchase not found? Where's my data purchase? So set seed, purchase. Did we create purchase vector? Purchase data frame. Where's purchase data frame? Vanilla, oh, manually fitting. Am I in the answer key? No. Oh, this one here, right? Manually fit a vanilla partition model using the RPAR predicting using from all the predictors on the trained data set. Find the predicted value of the usage for someone who is not on the pay plan. Okay, so this is one of their X's. So X1, not on pay plan. The answer to pay plan equals new. On a day with daylight savings hours, Diosh. And cooling hours, this. I'm going to probably try to do not exactly the work you're doing. Heating hour, oh my gosh. So these are just all your what's-is. You may not use all these. You may not use all these. So these are just all your what's-is. You may not use all these. Oh, thank you. Yeah, just keep at it. Just, yeah. Oh, yeah, just do the full-on, go the full way with the mass option right there. We can just go, yeah. No, you can just go full and just remove user from channel. No timeout. You're one and you're done on that. You bot, are you doing that stuff? You're one, you're done. It's interesting. Sometimes it happens when we do Kahoots or something like that. It's been a little more lately, so I'm like, man, are they really all over YouTube to like be hitting up, like that? I mean, yeah. When did that one last minute? So here are the X's, right, Alexander? So what we need to do right here is, here's the R part. We're not going to quite do that. I'm gonna do a little bit differently. You want to have your train data. You want to have your so you want to have your train data. You want to use your holdout data to see how it does. So that's the usual like PROC, all that good stuff right there with predicting with your model. But let's go ahead and take the data. Survey 10. Are we predicting? We're predicting usage. So we'll do a quantitative variable. So what's interesting is we're actually doing stat 201 right now, and let's predict the weight of individuals. And tilde dot data equals, well, we basically give it to you right there. There we go. There's the R part. Let's store it into tree. And there's the tree. And then let's visualize the tree. And so here's our tree right here. So when you make predictions using the tree, what do you need to do? We're going to predict somebody's weight. We need to go through and look at their what variables here. Like everything over here is their what variables. Like I'd have to say first to you, how much do you want to weigh? I'm predicting somebody's weight. So the first question I'd ask you is how much do you want to weigh? It's using the default CP, that is correct. I think it is 0.01. So if we were to raise the CP, we'd get a smaller tree. So you go right here and go complexity parameter equals 0.1, and now you get a smaller tree, or complexity parameter very, very low. You're going to get one of your bigger trees. This, and there's a ridiculous tree. So you don't want to do that. So it's using, and I think you're right, the default complexity parameter is 0.01, and it'll show it right here. Complexity parameter, it doesn't show the default for it. That's a bummer. But I think you're right. The default complexity parameter is around 0.01. Either which way, we are using the default currently, and we could see if we get a similar tree with 0.01 and visualize the model then, and there it is. Now you could, it actually looks like it's not using the default because it's slightly different, or that's not the default. Maybe it is, yeah. What you can also do, check this, Alexander, if you use library rattle, which we showed in class, you can go here to fancy rplot, or fancy rplot tree. And this can make some trees a lot easier to view. It depends on the size. Petry's code right there is a little bit easier for big trees. This for smaller trees is a little bit easier to see, and you can see the no and the yes depending on the answer to, do you want to weigh more than 166? So I want to weigh about 175. So I would say this is, do you want to weigh less than 176? I'd say no. Do you want to weigh less than 196? Left is yes. Yes. Then it says I weigh 182 pounds. That's pretty darn close to what I weigh. And there's 165 individuals, which is 24% of the original 699 people. Does this make sense, Alexander, right here? Like, I don't want to do your exact question, but these are the answers you would use to figure out the pathway to go in the tree. So you have to go to each question right here and then decide left or right based on the response in the question. And then you have to read it like, do you desire to weigh less than 166? I want to weigh 175, so no. Do you desire to weigh less than 196? Yes. We could also predict my height here pretty quickly. And so I like using the rattle. And so there it is right here. Do you want to weigh less than 155? No. Do you want to weigh less than 176? So I want to 175. Yes, yes. Are you gender female? No. So it says I am 71 inches tall. I'm 75 inches tall. So we don't use all the variables. So correct. If you notice right here, the tree can vary because if you put in just whatever, I think GPA is in this one. So here's the GPA tree. As you can tell, sometimes it's better with different packages. It's just a different way of visualizing it. You just use what's in exactly. I think that's maybe where some of the confusion is. This one might be easier to do with this one. How much do you weigh greater than or equal to 145? Yes. How many times do you text per day? I actually do you text less than that? I do. Do you think you're funnier than less than 33%? No. So there we go. I almost got to one of the lowest GPAs. It said I had about a 2.83. That's probably pretty close. Yeah, so you don't use all the X's. You just use what's in the tree, and this would help you answer when you get to one of these nodes right here. So these are the branches right here. These are the leaves at the bottom. And so, yeah, you just go through the tree and answer the questions based on the information given. You don't have to use all of them, but yeah, good question. So I think that makes sense now, right, Alexander? Like, would you say this question makes a lot more sense and you just go through the tree saying, oh, this, use this. Hopefully it is like, well, now we just do this. The left is yes. It usually should say in the tree. I think pretty much all trees do that. It's just the way it codes it. And then be careful though, because it could be greater than, equal to, like the way it says it, you just read it as a question. Like that right there says, is weight greater than or equal to 145? My weight is greater than or equal to 145. Yes. Are your texts per day less than 9? Yes. My texts per days are less than 9. Yeah. So just read it as a question, then answer the question yourself. Like, is this? And then, yeah. So it's just, yeah, really good practice. Great job, Alexander. Good work. We'll do the heads, tails question. Let's check that out. Okay, heads, tails question. Let's do this on the exam review. Remember, review 2, I have the videos up to all the questions, but let's do the review 2 question. Let's check it out. Stat 201. Test review. Question 1. Let's go check it out. Here we go. So here we are on the review page. The review page has videos going over each one. Let's reload it. Loading the review page. The review page has videos, or should have videos. Gonna load. That's weird. Dun, dun, dun. Well, I hope it works. Should have the videos. It did have them a moment ago, but we'll find out. My internet's not working. Oh, I'm still connected streaming. So let's go look at the practice exam right here. It does open. That's good. And the practice exam has the following question. We have a fair two-sided coin. Let's go look at that. With a fair two-sided coin, if the first 3 flips are heads, tails. What is the probability the 4th flip will be tails? Coin flips are all what of each other? And it's fair, so probability of tails is 50%. Probability of heads is 50%. So the 4th tails would have a probability of what? The 4th tails would have a probability of 50%. But be careful. Remember, each flip is independent. So if there were 3 prior flips, these prior events don't matter. So anything that happened here, this current event would be independent of the previous events. Does that make sense? So it's just basically it's saying you have a coin, things have happened in the past. What's the probability of the coin coming up tails? The things that happened in the past are independent of what is currently going to happen because the coin's trial each time is independent of past flips. Does that make sense there, Jalen, to say each trial of the coin is independent of previous occurrences? So what's the probability on the 4th flip it comes up tails? Well, it would just be 50% when we flip the coin on the 4th time. For the next one, it's a little bit different, though. It says, what's the probability of getting 5 tails in a row? 5 tails in a row would be the probability of tails, and then tails, and then tails, and then tails, and then tails. So what is the probability of getting tails and tails and tails and tails and tails? So if you see the keyword right there, great job, Ethan. We're doing the multiplication rule right here. And the multiplication rule requires, I don't know why the videos aren't loading. The multiplication rule requires, let me click the link again here. The multiplication rule requires that each of the things, I wonder if the videos are broken for the moment. The multiplication rule requires that they are independent right here. So when we do this probability right here, we want to multiply each of the probabilities by each other. So let's go back to the question, and we would do the probability of tails times the probability of tails times the probability of tails times the probability of tails, and there we go. So this would be 0.5, so it would be 2.5, 0.125, 0.0625, 0.03125. It's harder to subtract for that. 0.01625? No, 0.01565. Got it. And preferably probably just do 0.5, 2, 3, 4, 5, and there it is right there. How are we doing on that, Jalen? Does that make sense? And I might go look up the links to the videos. Oh, there they are. So definitely check out this playlist right here. And I'll drop it in the chat. That's the full. It does. Nice. Check out this link right here.
For this first question, we are going to look at a two-sided coin, and we're going to flip it. Now, this is a fair two-sided coin, which means it has a 50% probability of heads and a 50% probability of tails. If the first 3 coin flips come up tails, what is the probability that the 4th coin flip comes up tails? The important thing to note here is that the coin is going to have independent trials. Each one of these coin flips will not be dependent on what it was previously. So although you've gotten tails 3 times in a row, you will not have this 4th flip influenced by the previous flips. So the probability of getting tails on your 4th flip is 50%. Now this goes into the law of averages, which is a fallacy. Someone might say, you flipped tails a whole bunch. Don't you think it's time for heads to come up? Well, if you looked at it the incorrect way and thought that the events of the past influence the events of the future, you might say yes. But remember, you're just flipping the coin a 4th time. The coin does not care what happened the first 3 times. The coin has a 50-50 shot of coming up tails, so on the 4th coin flip, it will have a 50% chance of coming up tails. The next question kind of expands upon this a little bit, and now this time we want to look at the probability of getting tails 5 times in a row. This time you're going to flip a coin and it's going to come up tails, 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 and tails. And it's important to realize what's going on right here. You are getting tails 5 times in a row, which seems kind of unlikely. Each time you flip the coin, it has a 50% probability of coming up tails. So the probability of getting tails, and then tails, and then tails, and then tails, and then tails would be 0.5 to the 5th power. And what this actually is the multiplication rule, because each flip of the coin is an independent trial. So when we multiply together 0.5 by 0.5 and do it 5 times onto itself, we are actually doing 0.5 to the 5th power, and we have the probability of getting 5 tails in a row. These questions go over some important rules right here in a row.
This is so crazy. I just remembered making this video, and I had to do a few takes of this because on the last moments of making these videos, I read the probability wrong either once or twice. And I was like, we have the probability of 0.0325. And I was like, and I don't know why I didn't just edit the audio. I guess I wasn't that good at audio editing back then. But I remember doing them in one take. And I remember that pause because I'm like, why didn't I read the probability? And I showed it on the screen, but I was like, oh yeah, that was like, I remember that take. I remember like messing up saying the number and then redoing the video. Be like, I'll just do a better take and get it right and do it in one take. That's oftentimes my theory is like, do it in one take, less editing, better. Because I mean, it's only 3 minutes worth of talking. It's like, you just got to talk for 3 minutes and say everything perfectly. I mean, is it perfect? It's not perfect. I was catching things. But check out these videos. See, all those e's, try to remove those from your vocabulary. But filler words. There's reviews going over multiple things. Kahoots, reviews. Oh my gosh, who was that?
We almost had.
Is that Jason?
Oh, imported. Entered plus 2002 squared. A few sets of batteries left, and I was like, I'm gonna be going a while tonight. We're gonna be doing a lot of reviewing. So, and I actually heard it kind of go. So thank you to Jason once again for bringing it. I'm using a wireless mic here, and the receiver ran out. How's batteries?
That's so cool.
Yeah.
Hey, always remember, people,
Go ahead.
you need batteries. You gotta have batteries. So there you go. You need batteries.
I gotta send this to Jason. Oh man. All right. Well, I'm having some fun right here. I'm gonna send that to Jason and be like, who is that? Who's that helping out with Stat 201? Man. Well, be practicing, be reviewing. I'll see everyone later. I've got some meetings, and keep up the good work. Have a great day, everyone. Bye for now. Bye.